This is Engineering Statistics and Linear Algebra 18 EC 44, Module 2, Lecture 1. We were discussing about the multiple random variables, that is two different quantities, Bivariate Cdf, and the PDF is what we were discussing. So in this we took the introduction and then we discussed about the bivariate cumulative distribution function and the bivariate probability density function, right? And we took up some of the examples also corresponding to that. And then now we need to go for what is known as independence. So if we have random variables, two different random variables x and y, then they are independent if we have the joint probability function which separates. That means the distribution function, if you take like this, now this we know how we have written f of x, y, x comma y in 3.1 is what we have written over here, right? This is the 3.1 over here where we have put x less than x intersection y less than y. Now separating this out, we'll get p of x less than or equal to x multiplied by p of y less than y. So in that case, we say that they are said to be independent. That's what we have written there. Okay. So we have separated them out, and this is nothing but fxx, and this is nothing but fyy, and that is what we have here. Similar, that just means that independence will be the what you call case when the what you call bivariate probability distribution, cumulative distribution function, bivariate cumulative distribution function is equal to the multiplication of the individual cumulative distribution functions of each of the variables x and y. Similarly, the bivariate PDF also can be separated like this, where we can differentiate the quantity can be differentiated, and this is with respect to x and this is with respect to y, and hence we'll get that as fxx and fyy. And that again gives us that the probability density function also can be, the bivariate probability density function can also be written as the multiplication of individual probability density functions of each of the two random variables. Let us take some examples over here. Now, if we let us refer to the 3.7a and its bivariate PDF, which is there in 3.15. And if we substitute this 3.15 to 3.17, then we'll get that. So 3.7a is this figure, 3.7a is this figure. Then we have the 3.7a okay, 3.15 and 3.17. 3.15 is here. This is 3.15. This has to be substituted in the 3.17. So this is f of xy, x comma y equal to 1 within the range 0 to 1 for both x and y. And this has to be substituted in 3.17. So 3.17 is here. So we have f of x, y, x comma y, where that quantity has to be substituted. And we'll get the value which is equal to f of x. Now limits for this will be 0 to 1 only, because otherwise it is not existing. The f of x, y, x comma y is not existing in the other values other than 0 to 1 for y. And hence we will get here 0 to 1 dy equal to this quantity itself. If you integrate, you will get equal to 1, because dy integration is y, limits 1 and 0, and that will be 1 within the range 0 and 1. Similarly, fyy is also the same thing, except that the 3.16 has to be substituted in the 3.18. 3.16 has to be substituted in 3.18. to get the final value, something which is something like this. So if you multiply these two quantities, you will get back this value, and this value is nothing but the value f of xy x comma y. Therefore, we will have that because this equation is satisfied, x, y are said to be independent. X, y are said to be independent. Let us take the next example of 3.4. So wherein we will refer to the figure 3.8a, where we'll take the discrete probability density functions. The bivariate PDF, which is considered in 3.16, is what we'll take, and again we'll try to substitute the 3.16 into the 3.17. So 3.8a figure, if you see over here, this is 3.8a, and corresponding to this, we have 3.16 over here. This, if you substitute in 3.17, here you will get the value of xx. Now, you are trying to integrate it with respect to y, the quantity which is there over here. So integral corresponding to del y will be equal to 1, integral corresponding to this del y will be equal to 1, integral corresponding to this del y minus 1 also will be equal to 1, integral corresponding to del y minus 1 also will be equal to 1. So therefore, we are left with 1 by 4 del x here and 1 by 4 del x here. Together it will become 1 by 2 del x. Similarly, we are left with 1 by 4 del x minus 1 here, 1 by 4 del x minus 1 here. Together we are left with, we'll have 1 by 2 del x minus 1. Hence, we will get the value which is, something like this. 1 by 4 del x plus 1 by 4 del x minus 1. Similarly, the PDF for y can also be obtained by substituting 3.16 into 3.18, you will get fyy. Again, that will be half of del y plus half of del y minus 1. If you take the product of these two, right? If you take the product of these two, that's what we have done here. We'll get this, and again we see that that's equal to f of xy, x comma y. And because we satisfy this equation, we say that x, y are independent of each other. Let us take the example of 3.5, where we'll consider the f of xy is equal to this, quite a big equation over here. And to solve this, we need to, write this as the technique of complete squares. Complete squares. That means x square minus 1.4xy plus y square can be written like this. Can be written equal to this quantity. Equal to this quantity. Then you just integrate this with respect to y. Integrate this with respect to y, you will get fxx. Integrate this with respect to x, you will get fyy. Okay, so integrate this with respect to y over here, then the x quantity can be just taken out outside, and the inside one has to be integrated. To integrate that, we'll substitute it as this whole quantity, that is root of this quantity. The root of this whole quantity can be considered as u by root 2. U by root 2 equal to that whole quantity. So that we'll get in the proper format like this. Okay, our proper format minus u squared by 2. So you'll get it as minus u squared by 2, and you have taken it out. And now this quantity is nothing but root of 2 into pi. 2 and pi both will come in the root. So if you simplify this, this will become 1.025 whole root. Then if you simplify this quantity, then we'll get 1 by root of 2 pi e to the power of minus x squared by 2. In the same way, fyy also can be found out by, again, proper separation of the variables, and we'll get the value as minus infinity to infinity. Similarly, if you integrate f of xy, x comma y in the limits, in both the regions x and y between minus infinity to infinity, that quantity will turn out to be 1. If you multiply the two PDFs, f of x and f of y, you are going to get the quantity which is something like this: 1 by 2 pi exponential of minus x square plus y squared by 2. So the result of that multiplication will be what you call does not equal the original bivariate PDF in the 3.25. This is something different from what we have in the earlier equation over here. Therefore, we say that f of x multiplied f of x multiplied by f of y is not equal to f of xy. Therefore, xy are not independent. Then we come to the multivariate density function, more than two variables. Till now, we consider two variables. You can extend that logic for the multivariate density functions. So here we have n number of variables. So the joint, so to say, PDF of all the n variables will be the nth differentiation over here for each one of the variable x1, x2, x3, xn of the cumulative joint cumulative distribution function. Similarly, the what you call inverse property also holds good. That is, the cumulative joint cumulative distribution function will be the integral of n integrals of the joint distribution, the joint density function, probability density function. Also, the area under the curve, total area under the curve should be equal to 1. That's why integrating it from minus infinity to infinity, the whole of the PDF will give us the value of 1. Other extensions such as 3.6, 3.7, 3.17, 3.18, which we have considered, can also be written for the multivariate case, which we have written for bivariate. So 3.6, 3.7. So 3.6 we have written here fxy infinity comma y, that is equal to fyy. Fxy x comma infinity is equal to fxx. This is the cumulative distribution function. Similarly, the 3.17 and 18. So this is the what you call PDFs. Fxx is equal to integral minus infinity fxy x comma y. We are writing the PDF like this, and similarly this PDF fyy is equal to integral of this. Can also be written for multivariate random variables. Now let us take an example of the what you call whatever theory we have studied. So here it is given that the joint probability density function is equal to C, a constant between the region of x equals 0 to 3 and for y 0 to 4 and 0 otherwise. Okay. So what is the value of the constant C? So we need to integrate this, okay, for dx and dy within the limits 0 to 3 and 0 to 4 respectively, and that's what we have written here. And if you try to simplify this, you'll get 12c, that will be equal to 1. This total probability should be equal to 1, and 12c should be equal to 1, and that will give 4 into 3 will be 12. 12c will be equal to 1, and c will be equal to 1 by 12. Then the individual probability density function fxx and fyy can be found out by integrating the fxy x comma y with respect to y and with respect to x respectively, and within the corresponding limits again. So hence we'll get the value of fxy is equal to c, and that is 1 by 12. C is equal to 1 by 12, and 1 by 12 comes out, and 0 to 4 dy will give us 1 by 3 within the limits of 0 to 3. Similarly, fyy will be 1 by 12, integral 0 to 3 dx equal to 1 by 4 within the limits 0 to 4. Similarly, next we need to find the distribution function xy between the limits 0 to 3 and 0 to 4. So therefore, we can write 0 to x and 0 to y here, du dy. This is c is 1 by 12, and you'll get the value as xy by 12 between the range 0 to 3 and 0 to 4. If you include the 3 also, then it will be equal to 1. This whole thing will be equal to 1, whereas we are not including the value of 3 over there. So we are taking in the range 0 to 3 only. Therefore, at that time, it will be xy divided by 12. So f of x, the single random variable distribution function will be equal to fxy, that is the joint one, with y equal to infinity. But we can't take y equal to infinity because the value of y is between the range 0 to 4. Therefore, we substitute 4 for y over here. So if you substitute for y 4 here, you will get x into 4 by 12, that is x by 12. Similarly, fyy will be equal to fxy infinity comma y, and that is giving us the value. Again, infinity cannot be considered because the value of x is only between 0 to 3. Upper limit is 3 over here, and if you substitute this 3 into this equation for x over here, you'll get 3y by 12, that is y by 4, and that is the value here, and that's within the range 0 less than y less than 4. So if you see here, if you multiply these two quantities, x by 3 and y by 4, you'll get xy by 12. Similarly, if you multiply these two quantities, you'll get 1 by 12. Therefore, xy are said to be independent, right? Xy are said to be independent. So